Have any of you started the design project? I'm just curious, have you tried the design project? Okay, that's good. Because I think we're going to have an HKN survey later today, but one of the questions, what we actually, our EECS program is ABET accredited, so one of the things we have to do for accreditation is get feedback from the students. And EE130 is actually a design course, one of the courses you can take to fulfill your design requirement. So that's why you're going to be asked to answer a question in addition to the HKN survey related to the ABET process. Anyway, the question is regarding whether or not you had a chance to learn to design something, but you haven't finished your design project yet. You can imagine that you will have finished it by the end of the class, right? Okay, so on the quiz, I guess the score was, the average score was a little bit higher even than quiz 4, so that's good. It's kind of hard to tell. I tried to use the rainbow colors, but the quiz 5 scores are the darkest color here, the darkest bar. Okay, so dark blue. So I think you all, as a group, did well. And I know, I am going to drop your lowest quiz score out of 6 at the end of when I determine your course grades. Okay. Let's see, were there any leftover questions from the quiz or advanced MOSFET structures? Okay, great. So today we're going to start talking about the bipolar junction transistor. And anyway, my wireless internet doesn't work here. Okay, so BJT is actually it's the first transistor that was used in integrated circuits a long time ago. But because it actually is not as energy efficient as a MOS transistor, and is not as easy to scale to really, really small dimensions. Well, actually, it's not as energy efficient, so it uses more power. And so you can't really fit as many of them per unit area. You can't cram them in tightly together. And so for those reasons, BJTs are not the dominant transistor structure used in integrated circuits today. But they are still used in circuits where you want very high speed or high frequency operation, because a BJT, a bipolar junction transistor, does have much higher current gain than a MOSFET, or it can have higher gain than a MOSFET. And so that's good if you want high speed and high frequency operation. Okay? All right, so I'm just going to call it BJT from now on for bipolar junction transistor. So today's lecture will be just short. It'll cover chapter 10 in Pair A, just the fundamentals of a bipolar junction transistor. And for those of you who've taken EE105, I think you covered this type of transistor first. And usually we do cover it immediately after the PN junction because it's natural. We just take 2 PN junctions and make a bipolar junction transistor like this. So a BJT just comprises 2 PN junctions that are back to back. And actually, this is kind of inherent. This PNP structure is inherent in a MOSFET. And that's another reason why in the past we've always covered this device first. All right, so remember in a transistor, what we do is we have one control terminal. And we have one terminal where we're controlling the current or the voltage. And that determines the current flowing between the other 2 terminals. So usually we consider the control terminal in a BJT, the terminal that connects to the middle, the middle region, the base. Okay? So we apply a voltage or a current to the base, and that controls the current flowing between the other 2 terminals. The 2 other regions are the emitter and the collector. Okay, so one thing to notice here in a BJT structure is that it is not symmetric. So that's different than a MOSFET. So in a MOSFET, the source and drain regions generally in an integrated circuit look the same, right? You can't tell which side is the source or the drain, which heavily doped junction is the source or the drain until you see what voltages are applied to the MOSFET. But in a BJT, it's actually quite asymmetrically doped. The emitter is usually much more heavily doped than the collector. And by the end of this lecture, you'll qualitatively understand why. Also, the structure itself, typically, if you look at a cross-section, usually the emitter is a small PN junction. So let's say a P plus region here. And then we form that by diffusing a P-type, heavily doped P-type region into an oppositely doped N-type region. And then that N-type region actually is also diffused into a P-type substrate. Okay, so then we have metal contacts at the top surface, right? Basically, when you make an integrated circuit, you have metal contacts coming down to the surface of the silicon to connect the 3 terminals of the transistor. So we have usually a structure like this, a collector, the base, and the emitter contacts all coming from the top side. But you can see that the structure is completely, not symmetric between the emitter, geometrically as well as doping-wise. So what we're going to just cover in this class mostly is just the heart of the transistor, which is here, right? The P, N, P region. We want to see how the structure or how the transistor operates when we apply voltages between these regions at the heart of this structure. So we know that to get current into and out of the base, we have to flow through this resistive, doped silicon region. And to get current to flow in and out of the collector, usually what happens is we have a heavily doped sub-collector down here. So there's a heavily doped region here, and maybe a heavily doped, during the fabrication process, we have a heavily doped P-type region to the side, so we can actually get current flowing into, through this lower resistance pathway into and out of the metal contact at this top surface. So anyway, so this is a cross-section of a more realistic view of a bipolar junction transistor. And the subcollector and this P+ region here is really, to the side, is to make lower resistance contact to the collector. But in this class, we're just going to assume, for simplicity, that the PN junction is, the bipolar junction transistor is just a rectangular volume, and the area of the, so the area of this junction right here is the area of the emitter. That's just a rough estimate, right? Even though the real junction area includes this sidewalls and so on, we're just going to assume, okay, the area of the emitter, base emitter junction is just going to be the area here, and the area of the collector to base junction is just going to be the area of this junction there, right? But in reality, we know the area of the collector junction is actually much greater than the area of the emitter junction, okay? But for this class, you just need to understand qualitatively how BJT operates and how the performance changes with, let's say, the doping in the base and the width, or the width of this base region. Okay, so we have 2 PN junctions that are sandwiched back to back, forming a sandwich structure here. So we can either have a PNP or an NPN structure as a bipolar junction transistor. For the textbook PRA, we focus mainly on a PNP. Both PNP and NPN are used, but NPN is actually more common in an integrated circuit today. So there's what we call bi-CMOS technology, so where we integrate an NPN, usually it's an NPN BJT together with NMOS and PMOS transistors to get high speed and high speed where you need it, like in the RF radio frequency circuits, and then low power for the digital computation parts of your circuit. Okay, so let's see. These are the circuit symbols, just to illustrate. If we want to draw a transistor operating in a circuit, we usually use a circuit symbol. The way you delineate an emitter is with this arrow. So let's show right here. Okay, so the arrow usually indicates, the arrow indicates the emitter junction. Okay, otherwise the symbol kind of looks symmetric, right, between the emitter and collector. So the way you distinguish the emitter is with the arrowhead, and the direction of the arrow always points to the N-type material. Okay, so we know that we have an N-type base on the left and an N-type emitter on the right. Okay, so that's how we know if this is a PNP or an NPN bipolar junction transistor. All right, now our text, the main textbook for 130 defines current to be positive in these directions indicated by these arrows. So today, let's just focus on PNP. Okay, so these current directions are defined to be always so that IE, IB, and IC are all positive quantities. Okay, so the IEEE profession in convention, we actually usually define currents to be positive going into any terminal, but we're not following that convention. in this class, because of the textbook, we'll just define the currents to be flowing in the direction that they're normally, such that they're positive quantities, okay? All right, so the notation would be I sub B is the current flowing into or out of the base, depending on if it's NPN or PNP. IE is the current flowing in or out of the emitter, and I sub C is the current flowing into or out of the collector. And then these subscripts for the voltages, again, so VCB, so V sub CB is just the voltage difference between the collector and the base, and so on. So hopefully by now you're very comfortable with these conventions for the voltages, right? So the voltages are always defined to be a difference, the potential difference between two terminals. Okay, let's see what else. So I think that's okay. So hopefully you'll get used to this convention with some practice. Okay, so to understand how PN junction or BJT works, let's first review how PN junctions work. Okay, so I'm going to draw on the board here. So if we draw the current versus on a current on a linear scale versus the voltage applied to a PN junction, it'll look, in reverse bias, very little current flows, and under forward bias, significant current flows. It increases exponentially with voltage, right? Okay, so that's for forward bias. So forward bias current increases exponentially. So let's focus on reverse bias. Remember when we shine light, if we shine light on a PN junction diode, what happens to the reverse bias current? Increases in magnitude, okay? So basically this IV curve shifts down, all right? And why does the reverse bias current actually increase in magnitude when we shine light on a PN junction? We create what? Yeah, what kind of carriers? Minority or majority? Minority, very good. So basically, we can use light to increase the current, the reverse bias current flowing in a PN junction because we're introducing more minority carriers within one diffusion length of the depletion region. Now, what's another way you can introduce minority carriers? Oh, okay, let's review. What happens under forward bias? What's happening with minority carriers under forward bias? Huh? Yeah, you're basically injecting minority carriers into quasi-neutral regions, right? So when you lower the potential barrier with a forward bias, what you're allowing diffusion to occur, and you end up introducing excess minority carriers in the quasi-neutral regions, right? So the idea behind a bipolar junction transistor is that, okay, rather than using light to modulate the reverse bias current in a PN junction, why don't we just use a forward biased PN junction? Okay, so we use a forward biased PN junction to inject minority carriers into the base. And if the base is less than one diffusion length, those injected minority carriers can diffuse to the collector reverse bias PN junction and affect the collector current. Right? So basically, it's what we studied before. You can modulate the reverse bias current of a PN junction, but rather than shining light, you do it by injecting minority carriers electrically with a forward bias PN junction. Okay? So basically, that's the idea summarized here on this slide. Basically, instead of using light to inject or to create minority carriers within a diffusion length of the depletion region, we just forward bias a PN junction and inject minority carriers into the base. And that's it. Okay, so qualitatively then, how will the reverse bias current of this collector junction, how will that depend on the forward bias voltage on the emitter junction? So emitter is the PN junction that's emitting minority carriers into the base. Right? So as you increase the emitter voltage, how do you expect this collected minority carrier current to change? Exponentially, right? Because the forward bias current, you're exponentially increasing the number of minority carriers injected when you apply forward bias on the emitter junction. that means you're exponentially changing the current collected, at the collector junction. Okay, that's great. Okay, so how do we get gain? So it turns out that the gain is really defined to be, okay, can we control can we change the collector current by a large amount by only changing the base current by a small amount? In other words, how do we change the emitter current by a large amount by changing only the base current by only a small amount? Okay, so let's review here. So if we forward bias this base junction, okay, this base emitter junction, we'll have holes injected into the base because they become minority carriers in the n-type base. And then they diffuse across the quasi-neutral base. They make it to the depletion region of the collector junction, and they get swept across. So we want the number of holes injected into the base to be large compared to the base current. Okay. All right. So what comprises the base current? So let's look at the components of base current. So when we forward bias, okay. So this is VEB greater than 0. So this is forward bias, right, for the emitter junction. So when we forward bias the emitter junction, what determines like how much current is due to electrons being injected into the p side versus holes being injected into the n side? What determines that ratio? Like remember in a p-n junction diode, okay, so we have the current is proportional to the area, cross-sectional area of the junction, and it's going to depend on the charge of each electron and hole. Okay, so we have the diffusivity of the electrons injected into the p side, okay, and the gradient is proportional to the diffusion length of electrons in the p side. And then the equilibrium minority carrier concentration of electrons in the p side. And you have the similar term for holes. Okay, so you have one term in the, and this is exponential, right? There's an exponential factor here. Okay, so basically if you look at the current flowing across the junction for a forward biased p-n junction, you have one term due to holes flowing across the junction, and another term due to electrons flowing across the junction. Okay, so if you look at this, review the equation for p-n junction current, what determines the relative magnitude of the hole current versus the electron current? Doping. That's right, exactly. So if you want more holes to be injected across the junction for the same forward bias on the p-n junction of the base emitter junction, do you want the p side to be more heavily doped or the n side to be more heavily doped? P side, right? So yeah, so basically, hopefully that's kind of qualitatively intuitive, right? If you want more holes to flow across the junction than electrons across the junction, you want more p-type material, more heavily doped p-type material. So that's right, and that's exactly why this emitter is more heavily doped than the base. Okay, that's an important design parameter for a good bipolar junction transistor. So the emitter should be more heavily doped than the base. That way, this hole current will be larger than the electron current, and ideally, all of this hole current is collected to become the collector current, and so that's how you can get significant collector current for a relatively small input base current. Okay, so that's the current gain, right? So the DC current gain beta. Okay, so the symbol here is beta. It's defined to be the ratio of the collector current to the base current. And in order for that to be a large number, much greater than 1, typically about 100, you want the emitter to be doped more heavily than the base. Okay? Okay, so the base current is due, so the base current has two components. One is, okay, the base contact here is supplying electrons, right? So only majority carriers can flow into and out of the contact. So under forward bias, you have electrons flowing into the base. Some of them actually diffuse across the junction and constitute emitter current. Some of them recombine with holes as they diffuse in the base region. Okay, so if the base region is kind of long compared to the diffusion length, then some of those holes that are injected into the base region will recombine with electrons, and those electrons are supplied by the base as well. Okay, so in order to have large gain, we want to minimize IB. So we want to actually minimize this recombination. So how do we do that? How do we minimize recombination of electrons and holes in the base? Exactly. So John was saying we make the base very short. Now, short relative to diffusion length. That's right. So, yes, that's absolutely right. So you want the base region, the quasi-neutral base region, to be relatively short. And so that's typically what order, what size? Like the diffusion length is typically maybe 10 microns or more. So the base region is usually less than a micron. Okay. Very good. So those are the main components of current flow. So some of the holes that are supplied by the emitter contact, right? Holes flow in, right? Holes flow in here. Electrons flow in to the n-type region, and majority carriers only flow into and out of a metal contact. So you have holes flowing out of the collector. So some of the holes that are supplied to the emitter actually are lost due to recombination. The rest go into the collector and constitute collector current. Now the collector junction is, if it's reverse biased, there's going to be some, normally for any reverse biased junction, there will be some current flowing across that. So basically just minority carrier collection across the collector junction. So you'll have holes moving back into the p side and electrons collected back to the n side due to the reverse bias on that collector junction. And ideally, that reverse bias, leakage current of the p of the collector junction is relatively small. That's why the kind of small arrows on this diagram. Okay, so there are multiple components of current flow here. Does anybody have any questions about any of those? We just qualitatively, right? This is a qualitative kind of picture, and we're just going over qualitative understanding today. Okay, so we're just going to review to achieve high current gain. So that means beta DC, which is defined to be IC over IB. Injected minority carrier should not recombine within the quasi-neutral region. So that means the width of the base, let's be specific, the width of the quasi-neutral base region should be much less than the minority, I'm just going to write it out, minority carrier diffusion length. Okay? So the chances of recombining before it diffuses to the collector depletion region is small. Okay? So that guarantees that so IC will be as large as possible. The emitter junction is comprised almost entirely of carriers injected into the base. So that means that we want IB to be small. Okay, so we want IC to be large and IB to be small to have high gain. Okay, so this means that we need to dope the emitter more heavily than the base. Okay, what happens if we dope a semiconductor region too heavily, though? Huh? Band gap? Zener, okay. Well, what happens just to the band structure of a semiconductor? Yeah, band gap narrowing. So what happens to the Ni? Ni increases, right? Because the band gap goes down. So if you dope too heavily, what happens is band gap goes down, Ni goes up. So let's see. So we dope the, so electron term, right? So this term here, N sub A, if N sub A is too large for a PNP, for an emitter, then Ni will go up, right? This will increase. So that means that the electron component of current goes up, right? Which is actually not what you want, right? So you have to be a little careful that if you dope degenerately, you might get some counter effect. So there's some trade-off here. Okay, so maybe I think next week or maybe the last week we'll talk about. This is why today actually the high performance BJTs are actually heterojunction BJTs, heterojunction bipolar transistors. Basically, you have a slightly different semiconductor material for the base, which would be in this case corresponding to, yeah. So you have a smaller band gap material for the base. That way you can allow the emitter to be heavily doped and actually the base to be heavily doped, and you count on the the difference between Ni to help make sure that this lower requirement is fulfilled. Okay, so what we've been talking about so far is called the active mode of operation. So you have, I think on the next slide, yeah, no. Okay. In a BJT, you have two PN junctions. Each PN junction could be biased either forward biased or reverse biased. So there's, in principle, there are 4 combinations of bias for the PN, two PN junctions. Okay, so we'll come back to that. But usually, if we want to use a bipolar junction transistor as an amplifier, then we want to bias the emitter forward biased, okay, and we want the collector to be reverse biased. So in this simple cartoon, the depletion region will be usually larger for the base collector junction compared to the emitter junction because the doping is more heavy for the emitter junction. Okay, so active mode. Okay, so active mode means forward biased emitter and nominally reverse biased collector. Okay, so I mean junction, right? The junction is reverse biased or forward biased. Okay, so I think this is a little redundant, but basically we want to, let's see, I don't want to use this pen. Okay, so if we have a forward biased emitter base junction, then hopefully we'll inject holes. It's p-type. But some of those holes, hopefully only a few of those holes, will die due to recombination with electrons. But you'll have a lot more holes, just like illustrated on the previous slide, going across. Okay, so that's one component of base current, right? So this is, which direction is base current flowing here? Should be this way to be positive, right? Because electrons are moving in. Okay, so base current comprises electrons recombining. It comprises electrons injected, okay, across the junction, because it's a p-n junction. You have electrons as well as holes diffusing across the junction. And you have this reverse saturation current in the collector junction. So remind me, which direction are electrons flowing here for number 3? Okay, so you have electrons that are minority carriers in the p-type region. They wander into the depletion region. Actually, yeah, which direction is the E field pointing here? P and P, you have minus, like negatively charged acceptors, and you have positively charged donors here. Electric field is pointing in this direction in the depletion region. So electrons are going to want to go to the left, right? So if you have thermally generated electron hole pairs, minority carriers in the collector, and the minority carriers wander into the depletion region, they'll just get swept across here. So actually, that's why this third bullet says, basically this third component of current subtracts from the magnitude of the base current, right? It's actually reducing the base current. So this is actually not bad for getting small base current. And then recombination. So remember some non-idealities of p-n junctions. So when you forward bias a p-n junction, not all of the current, I mean, so that, yes, that will lower the barrier to allow diffusion across the junction, but some of those carriers can actually recombine in the depletion region, so you can actually end up some electrons recombining with some holes, recombining. That's just a non-ideal effect that shows up at low bias, right? Low forward bias that becomes significant. Okay, so this is like every component now of base current. So the key is we want to sort of minimize 1, 2, and 4. Number 3, I guess, doesn't hurt to reduce the base current, to maximize gain. Okay? Okay, so how do we use a BJT in a circuit? In this class, we'll just focus on 2 applications. One is as a switch, which is actually the last application. Again, a BJT can be used as a switch. When you turn it on, it'll conduct current and discharge the output voltage down to whatever the emitter voltage is. So it's kind of like a MOSFET. You just can close a switch to pass a low voltage or a high voltage, okay, between the collector and the emitter. But actually, a BJT is used more often for an amplifier. Okay, so for an amplifier, we care to look at the BJT current versus output voltage characteristic as shown here. So this is the more common configuration, circuit configuration used for a BJT. Okay, but let me just define. I think in EE105 you've seen this, but you have a 3-terminal transistor, and you apply the input signal, the input information signal, like a voltage signal or a current signal, between 2 terminals, and then you take the output signal between 2 terminals. So one of those 3 terminals has to be common between the input and the output. So that's why we have these configurations called common base, where the input and output both share the base as a common reference terminal, or you have common emitter, where the input and output terminals share the emitter as a common terminal. So let's focus on common emitter. So these characteristics here are for common emitter. Okay, so these are, output characteristics. Right, so this is the input. The input is applied between the base and emitter. The output current is the collector current, and the output voltage is the voltage difference between the emitter and the collector. Okay, so that's why we plot collector current versus BEC. Okay, that's why it's called output characteristics. Okay, but the current flowing in the collector depends on the input voltage, right? So that's why you have actually multiple curves for multiple input voltages. And actually, it's easier to plot it for multiple input currents. Okay, so just like for the MOSFET, we plotted the output characteristics, right? The output, the drain current as a function of the drain voltage. But we had to plot a separate curve for each gate voltage. Here, same thing, we're plotting the output current versus the output voltage, but for different values of input current in this case. Okay? So just like in the BJT, okay, so let's look at this. VEC. So VEC, the output voltage, is equal to VEB plus VBC. Right? That's just the definition here. Okay, so the output voltage is just the difference between the collector voltage and the emitter voltage. But you can break that down into VEB and VBC. Okay, so VBC, that's going to be the reverse in the output, in the active mode. This will be the reverse bias on, well, it's normally reverse bias, right, on the collector junction. Okay, so let's go back to the IV curve for a PN junction. How does the reverse bias current depend on the reverse bias voltage, ideally? It doesn't, right? And that's exactly why this current is flat, right? Because if IB is fixed, right, for each curve, IB is fixed. So ideally, that means that VEB is fixed, right? So we're drawing a curve for a fixed value of the gate the base voltage, or equivalently, it's the same. It is a fixed value of base current, right? So we're not, for each curve, we're not changing VEB when we scan, VEC. So in this on this plot, as you're going from 0 to 20 volts for VEC, VEB is not changing. The only thing that's changing is VBC, right? The only thing that's changing is the reverse bias on your collector junction, and we know ideally, as you change the reverse bias on a PN junction, the current doesn't change. Okay, so that's why ideally, the current is going to be nicely saturated, very flat for BJT, and you only change the output current by changing the input voltage, or equivalently this input current. Okay, so looking at this plot, this is an example of a simple quiz question. You might be asked, if I gave you this plot, can you estimate what beta is, the current gain? Just roughly. You might want to take a look at this curve. Yeah, right, so it's 10 milliamps divided by 30 microamps. Actually, I don't even know what is that? Is that like 300? Is that 300? Yeah, it's 300, right? Anyway, it's pretty large, right? So it's on the order of 100. Okay, so yeah, I usually give simpler calculation than that. Okay, so you can see that there's current gain here. Okay? So by applying this very small current signal, if you want to change the voltage, the current by tens of microamps, the amount of voltage change you need at the input, VEB, is very small. So for a very small voltage signal at the input, you can get a large change in current. And usually what happens is then we connect this to a resistor. Yeah, this is, that's interesting. Okay, so what we usually do is we connect a resistor to the output, and so the voltage drop across that resistor, this load resistor, can change quite a bit compared to the voltage change at the input, right? So you get some signal gain that way. Okay. Okay, so this plot, this is from Perret textbook. On the left, it just shows you just 4 quadrants, right? 4 possible combinations of PN junction biases. So each PN junction can be either forward biased or reverse biased. And so if you have the emitter junction forward biased and the collector junction reverse biased, or actually we still consider to be active mode, if the collector junction is actually zero biased or weakly forward biased, it's still considered active mode. Okay, so let's look at this here. Okay, so if the base collector junction is zero biased, they have some built-in electric field, right? And so even if you have zero bias on this base collector junction, there will be a built-in potential field. So even if you have minority carriers injected into the base and they wander to the depletion region, they'll still be collected and still result in collector current. So the collector junction doesn't have to be reverse biased, even zero bias, it can collect minority carriers injected into the base. And actually, that's always the case. So even if the collector junction is forward biased, it will still collect these minority carriers that are injected into the base. What happens is if you forward bias the collector current, now you'll start to inject holes into the base in the opposite direction. You'll start to cancel out the the effect of the holes injected from the emitter. So that's why eventually, if you forward bias, right, if you're going in this direction, if VCE is like going in this direction, you're basically starting to forward bias your collector junction. Okay, and once you start forward biasing your collector junction, that sort of counteracts, the forward bias of the emitter junction. And so that's why the total collector current goes down, right? Because now you're injecting holes like going the other direction, subtracting from the collector current. So eventually, then, it goes to zero when you have no bias, no net bias across the collector and emitter. Okay, but even for a while, because the current depends exponentially in the forward bias, depends exponentially on bias. So the current due to emitter, the injection from the emitter, can still be orders of magnitude larger than the current due to a forward biased collector until the collector is strongly forward biased. That's why, as long as the collector is not strongly forward biased, we still consider it to be active mode operation. Okay, now cutoff, if you want to use a BJT as a switch, open and closed switch, then you have to switch between cutoff mode and saturation mode. So cutoff mode means that both junctions are reverse biased. Okay, so if both PN junctions are reverse biased, then ideally only leakage current, reverse biased junction leakage current flows in any of the terminals. Okay, so for digital applications, we actually, so this is basically switching, right? If you want to use a BJT as a switch, then we actually usually try to operate between cutoff when the switch is open, okay, it's no current flowing, and saturation when a lot of current is flowing, but very, very small voltage is dropped. Okay, so let's see. So so here, saturation is in this regime where both junctions are forward biased. Okay, now when you actually have a switch, I'm just going to draw a little cartoon of a switch. Okay, so let's say you have some voltage, I don't know, some output voltage. Okay, you want to, when the BJT is turned on, you want it to act as a closed switch. But when it's closed, so ideally, if you have an ideal switch, what is the voltage drop across the closed switch, ideally? 0. You don't really want to lose any voltage across a closed switch. Okay, so that's why, see, the output voltage here in saturation is relatively low, right? So that's why when we use a BJT as a switch, we want to switch from, in the on state, we want to operate in the saturation regime because the voltage difference, VCE or VEC, will be small, right, across the output of this BJT. But if we want to use it as an amplifier, we just only operate it in the active regime. So we operate out here in the active regime as an amplifier. And then we go between cutoff. Okay, so remember when a transistor is off, usually what is the output voltage? Like we have an open circuit. If the switch is off, usually we only need a switch if there's a large voltage difference that we're trying to prevent from passing through. So cutoff, we usually operate with 0 current, ideally, but with large voltage across. And so usually when we operate a BJT as a switch, we're operating between cutoff when the switch is open to saturation when the switch is closed. In other words, large voltage drop across the switch or small voltage drop across the switch. Okay? So those are the regimes of operation for a BJT. Okay, so in the active mode, when we use it as an amplifier, if we just make a little change in the input current or input voltage, we can have a large change in the output current and therefore output voltage. Okay, so let's just introduce the BJT. Next time we're going to actually derive equations. So let's just remind you what the each PN junction kind of looks like. Okay, so we have a PNP structure. So remember I mentioned you shouldn't, the main thing is you should keep track of the total potential barrier heights, right? So to tell if a junction is forward biased or reverse biased. So if a junction is forward biased, oh, this is at equilibrium. Okay. Okay, so let's start with equilibrium. In equilibrium, we draw there's no voltage applied anywhere, so a single Fermi level, okay? And we have p-type material on the left, so the conduction band, the valence band is closer to the Fermi level, right? So this is P plus. And then in the collector, we have p-type material, not as heavily doped as emitter. So we also, but notice the valence band is closer to the Fermi level than the conduction band, right, because it's p-type. Okay, so it's just less heavily doped p-type collector than the emitter. So overall, between the emitter and collector, you're going to have a built-in potential difference, right? Because the valence band edge in the collector is not at the same level as the valence band edge in the emitter. In between, we have N-type material that's not as heavily doped as the P-type emitter. Okay, so the separation between the Fermi level and the conduction band is a little bit bigger than, compared to the Fermi level separation from the band edge in the emitter. Okay, and ideally, can you tell me, is this a one-sided emitter junction or not? It's one-sided, right? Because the curvature is, so most of the depletion regions on the lightly doped side, so you have only curvature this way. Now in the collector, it's not quite one-sided. I mean, it is certainly more heavily doped base than collector, but you see it has a little bit of upward curvature here before it turns over like this. Okay. So if the base region is not super narrow, you'll have a quasi-neutral region, where the bands are flat like this. Okay. All right. So basically, you could just draw a BJT energy band diagram like this. It's easiest to start with the equilibrium band diagram. So some definitions here: the quasi-neutral base width, we're just going to call W. Okay, so that's an important design parameter for BJT. And I think that's pretty much all you need to know. So in equilibrium, it might be easiest to start with the charge density profile, but you have depletion regions at the emitter junction, a depletion region at the collector junction. You can assume here a step junction profile. So use the depletion approximation to get, okay, so let's see. So this would be Q times N base. Okay, same thing here, Q times N base. And this would be minus Q times N collector minus Q times N emitter. So the subscripts now for doping, we have to delineate which region of the BJT we're talking about. So emitter doping is always, emitter, anything associated with the emitter has a subscript capital E. Anything to do with the base subscript is capital B. And anything to do with the collector subscript capital C. Okay, so qualitatively, you should know that the slope, right? The slope here is proportional to minus Q, to the charge density, right? So it's minus Q N E. Right? So that's why it's very negative, and it's steep compared, much steeper than this positive slope here. Right? So just remember the slopes are dictated by the dopant concentrations. And then you integrate the electric field distribution and invert it, right? It's negative sign, to get the electrostatic potential profile. Now, electrostatic potential profile just looks like that band diagram, but just flipped. Okay? Okay, and as I mentioned, there's a difference here due to the difference in doping concentration between the collector and the emitter. Right? So if the collector is doped like 100 times less heavily than the emitter, what would be this difference? Now, it's 120 millivolts, right? I mean, if there's 2 orders of magnitude difference, right? 60 millivolts per decade of change in doping, right? For this would be for NE over NC is equal to 100, right? Okay, so qualitatively, let me explain. I guess maybe we don't really explain until later, but why, does anybody remember, or maybe from 105, why is the collector doped more lightly than the emitter? The body effect, yeah. So basically, okay, so when we want to use a BJT as an amplifier, remember I mentioned for a MOSFET, so here's the output current. So MOSFET and a BJT are used similarly. So if you plot output current versus output voltage, okay, remember for a MOSFET we wanted to operate the transistors and amplifier out here in the saturation regime. So remember I had mentioned the small signal model, that if you have a slope here due to channel length modulation or drain-induced barrier lowering, that slope is actually bad for gain, for small signal gain. Okay? So we have the same thing that could happen here. For BJT, if the base is, well, okay, for BJT, you can actually have a slope here. Right, okay, you can have a slope. And that slope, Okay, so as you go to higher and higher output voltage, what you're doing is you're reverse biasing your collector junction more and more. If you reverse bias your collector junction more and more, what are you doing to the base, with the width of this depletion region? You're increasing it, right? You're increasing the width of this depletion region when you reverse bias this collector more and more. So basically then you're widening the depletion region while you increase the output voltage. And if the base width is getting narrower, the diffusion gradient is getting steeper, right? So basically this is called base width modulation, this quasi-neutral base width modulation. So basically you really don't want the depletion, you don't want much depletion of the base to have this base width modulation effect, right? So to minimize this effect, you want to keep the quasi-neutral base width kind of constant as you change the output voltage. In other words, you want to keep it constant as you change the reverse bias on the collector junction. And for that reason, you want the collector to be more lightly doped than the base so that most of the depletion region is in the collector, not in the base, to minimize this base width modulation effect. Okay, so the collector basically has to be more lightly doped than the base, which has to be more lightly doped than the emitter. And that's why a BJT inherently, if you want good gain, you basically want an asymmetric structure. Okay? So a simple question that sometimes is asked is, well, can you take a bipolar junction transistor and mix up the emitter and collector terminals? I mean, would it work very well as an amplifier if you reverse the roles of the collector and emitter? It wouldn't, right? Because the collector is more lightly doped than the base, so the ratio of current, holes injected into the base versus electrons injected into the base, into the emitter is not going to be good. Okay, so let's wrap up here. So the performance parameters we're going to define qualitatively this time, and next time we'll give you the formulas. Emitter injection efficiency, okay, or emitter efficiency. So this gamma is just defined to be the ratio of the carriers injected into the base versus carriers injected into the emitter. Right, so we want this to be much larger than this for high gain. So basically, the closer gamma is to 1, the better. Right, so this is emitter current due to holes, and this is the total emitter current at the bottom. Right, emitter current is due to electrons and holes diffusing across the junction. The base transport factor is basically the ratio of the current that you inject into the base and the current that actually gets collected. Sorry, the minority carrier current that's injected into the base versus the collector current the current that's collected, right? So the ratio of the holes collected to the ratio of holes injected. Okay, so that's IC due to P to the holes divided by IE due to holes. Okay, so that's a transport factor. In other words, and we like this ideally close to 1. And if you lose holes due to recombination in the base, then the transport factor will be less than 1. And then this common base DC current gain we define to be the product of gamma times the transport factor. Okay, so it's just definition. If you look at, the reason why it's defined this way is if you look at the common base configuration here, the output current is IC, input current is IE. Right? So if you take the ratio of those two, basically that's how you get that's how you get this definition of DC current gain, common base DC current gain. Okay, so this is just IC over IE. Okay. Collector current. So let's see. Collector current. So qualitatively, you have collector current due to holes that are collected from the base, but you also have a little bit of collector current due to this normal, reverse bias junction leakage. So if you plug in, so one thing, Kirchhoff's current law. Oh, sorry, wrong way. Which way does this go? Emitter. Well, okay. Usually we draw the emitter like on the top. Let's go back. Let's apply what you learned in EE40. Okay, let's write a simple equation. IE equals, the way these currents are defined, IB plus IC. Okay? This conservation of particles. So if we go back, IE equals IB plus IC, right? So that's where we just plug this in, right? And if we, oh yeah, so now we have IC on both the left and the right side, and we combine it, we can actually write this simple equation to relate IC and IB. And so you can see this is usually ideally negligible, so we can sort of discount that. So IB is, that's why it's approximately. If beta, the current gain is defined to be the ratio of the output current to the input current for common emitter configuration, then you can see that the alpha DC, the DC common base DC current gain is related to the common emitter current gain through this simple formula. So the closer alpha is to 1, the larger beta is. In other words, the higher your emitter injection efficiency and the transport factor, the higher your current gain. Okay, and I think that's it. Any questions? Except I don't know where the HKN guy is, but anyway. Question? Oh, there you are. Great. Okay. Any questions before the HKN survey? So next time we'll start deriving equations. Yeah. So the last 2 slides are just summary. And I think based on on the grading of the quizzes, from some of you have noticed, I actually didn't really take off for egregious calculation errors. So I think for the final exam, I'll try to minimize the calculations. But that means you're going to have to understand stuff qualitatively. But you don't need to write essays. But just make sure when you study for the finals that you do understand all of this qualitatively. Okay, for the next couple weeks. All right. If there are no other questions, I'll hand it over to the HKN officer. Thanks. Oh, and I'll hang around outside in case you want to pick up your quizzes afterwards.